This week we are talking about units of computation and tools of computation. And the first thing we are going to look at is the finite state machine. And based on this, we are going to define finite automata, deterministic and non-deterministic finite automata. And we'll see how language recognition is possible by finite automata. And based on this, we are going to actually classify languages. And these are formal languages. And we'll start with regular languages, and we will see what makes a language regular and what types of other languages are there, which we will see in Chomsky hierarchy. And we will conclude with the concept of a Turing machine and decidability and computability. Finite state machines are used to model the behavior of digital systems in general. These could be control systems, this could be computation systems, or you can also use finite state machines to actually represent procedures like algorithms or protocols, which we see usually in, for instance, computer networking. So what happens when certain input occurs and in what state you are in. According to these, you can decide on what action to take, for instance, what output to produce, if that's possible, and what kind of state transition you need to make. More formally, we define a finite state machine as this structure given here. And here these symbols represent, let's see, sigma is the input alphabet. So it consists, it's a set consisting of symbols, and gamma here is again a set of symbols, and it is the output alphabet. And in the most general sense, they do not need to overlap, but for most considerations, we might assume them to be equal or one the subset of the other, but not necessarily so. And the set S here is the set of states. This set is a finite set and it's a non-empty set. So you have at least one state and the number of states is finite. This is significant. Hence the name finite in the finite state machine. And S0 is a state, an element of the set of states S, and it is called the initial state. So it's the state in which the finite state machine starts operating. And the last two are two functions. F here is the state transition function. As you see, it has inputs in the form of ordered pairs, where the first one is the state and the second one is input symbol. So in a general sense, the next state is going to be determined by the current state and the input symbol. And of course, the output is a state, which signifies the next state. So usually these are clocked systems. So you have the concept of a time slot, and every slot you have a current state and an input symbol. Combine these together through the function f, you get a next state. And finally, g is the output function. And the output function may depend on the current state and the input symbol, or it can depend just on the current state. And these two define different types of machines. If the output depends on both the input state and, both the input symbol and the current state, this is called a Mealy machine. And if the output depends only on the current state, regardless of the input symbol, then we call this a Moore machine. There are certain differences between the two types, but essentially you can convert one to another. So theoretically speaking, they are equivalent in terms of computational capability. On the other hand, they have certain differences, obviously. In general, a Mealy machine has fewer states, so it might be easier to design Mealy type machines than the equivalent Moore machine. Or sometimes it could be easier to design the Moore machine if you lay out each state separately. Mealy machine also reacts faster to input, so this might be significant when designing time-sensitive systems. Here's an example. This is taken from our textbook by Rosen. This is a model of a vending machine, and the vending machine actually accepts inputs in the form of nickels or dimes or quarters. And it has orange juices and apple juices in it, and it has, apart from the coin input, it also has two buttons, an orange button and a red button. So there are 5 possible inputs. You have nickel, you have a dime, you have a quarter as possible inputs. You also have the orange button and red button. So these are the possible inputs. So your input set of input symbols is this set. So this is orange button and this is the red button. And the cost of the juices is 30 cents. And if the user inputs more than 30, you just return the excess amount immediately. And whenever one of the buttons, orange or red, is pressed, you just give out the desired juice. So here, this is your initial state, S0, and this signifies that this is actually the initial state. And each of these states here actually counts the number of 5s in the input. So you can have a 0, you can have 5, you can have 10, 15, 20, 25, and 30. Anything excess is going to be returned. So we can actually represent this machine in 6 states. So you start with this state with 0 input. Of course, from this, as I said, you have 5 possible inputs. If the buttons are pressed, either of them, you will do nothing because no money is input, so you are expecting money. Therefore, if orange or red are the inputs, then you stay in the same state and you do nothing. N here represents nothing. On the other hand, if a nickel is deposited, then you transit to S1, signifying that now the total amount input is 5. Or if, but of course the output is nothing, so you are still expecting more money. Or if a dime is input, you go to not S1, but S2, signifying that now you have 2 times 5 in your system. Or if the input is a quarter, 25, you go to state S5, signifying that the total amount in the machine is 25. So from each of these states, for instance, from S1, again, with any of these buttons, you do nothing and stay at the same state. But if money is input, from S1 with a nickel, you go to S2. From S2 with a nickel, you go to S3, etc., up to S6. And with dimes, you go to 2 next states. So S1 goes to S3, S2 goes to S4, etc. And with a quarter, S1 goes to S6 directly because now the total is 30. So what happens when you exceed 30, for instance, from S2, which means you have 10 cents in the machine, assume that a quarter is input. Then you go to state S6. You go to S6, and since the total is now 10 plus 25 is 35, you output a 5. So that's your change back to the user. And each of these, for instance, from S3, which it signifies that you have 15 in the machine, if you input a 25, you go to S6 and you output a 10, the change. And whenever you are in S6, first of all, you are ready to deposit the juice if required. But if more money is input, you just split them back. If 25 is input, you give 25 back. If 5 is input, you give 5 back. But if the orange button is pressed, you just give the orange juice. But now the money has been spent, so you go back to your initial state. So you see, in this way, using a finite state machine, we can model mathematically, can model the behavior of such a vending machine, and this makes it easier to design such systems.